Sure, go ahead.
For the, I'm unable to get into this week's module. It says access denied as soon as I click it to try to get the files.
Really? Is
Yeah, as
anybody
soon as
else
I click.
is anybody else having that problem?
Yeah, I am too.
Yeah,
Yeah.
Okay.
me too. It,
All right. Well, tell you what, I can't check it out where I am now because it won't let me log on. But when I get home, I'll check it out and I'll send you guys out an announcement when I get that fixed. I'll figure out what's going on with it. That's kind of weird. Thank you for letting me know that. So guys, it's getting near the time we need to think about having our first exam. It won't be this week. It won't be next week. I think it's the week after next. But I'll let you know. I'll check the schedule. It's usually the first week when we start lab. I think that's about 2 weeks from now. But I do have this list of study points, and if you printed out the PowerPoint presentations as notes, and as we went through the course, I mentioned certain things that you need to mark, certain slides you need to mark, and you want to study everything, but pay special attention to those slides. If you didn't mark those, you might want to go back through the videos that we made and just kind of review the videos while you have time on your side. Just briefly, in the first week of class, we talked about analog and digital. Well, there was an additional handout called the objective sheet for week 1. You want to make sure you go down and understand all the points on that sheet. If you have any questions between now and whenever I schedule the exam, let me know. But study that sheet. We have a lot of PowerPoint presentations. Again, like I said, pay special attention to the slides I told you to mark, but you want to make sure you review everything in all the PowerPoints that we went through. There's this classification of outputs, so that's a particular slide. The PowerPoint that deals with I/O, input-output modules, there's one slide on there that deals with classification of outputs. You want to look at that slide to make sure you can classify outputs. And then in the week 2 folder, there are some documents that I didn't specifically go over, but you're still responsible for the material. So the special I/O modules document. You'll see when you look at week 2, there's some documents there on Canvas on the website. You want to make sure you look at those documents. Again, I didn't go over those in class, but you're still responsible for the material on those sheets. So all I can say about that is make sure you look at everything on those sheets. And when you get a chance to go back and look at those, if you're not clear on what I'm talking about, let me know Wednesday or Friday, and I'll bring it up on our system.
Professor,
Yeah.
is there any way you could zoom in on that PDF?
You can, in the upper right-hand corner of your screen, there's a little box. I mean, upper left-hand corner, there's a purple box. If you click on that, there's a magnifying glass. You can make that bigger. You see what I'm saying?
I see it. All right, thank you.
Yeah, guys, if it's too small, just look up there in the upper left. There's a purple box. Click that, and you can make that. You can blow that sheet up and look at what I'm talking about. What else here? Number systems. Well, that should be fresh in your mind. We just went over number systems. So make sure you just kind of review the number system stuff. Students tend to make basic mistakes on base 8, base 16, octal, and hex. So I put a homework up. I know you told me you can't access this week's module on Canvas yet, but I did put a homework up there, and I'll show it to you before we leave today. And if you can do that homework sheet, you should be okay for what I'm going to ask you on the exam for hexadecimal and octal. Look at number 6 on that sheet. Look at number 6. Remember I told you, I said we look specifically at base 2. That's what computers use. Base 10, that's what we use. And the other bases like base 8 and base 16, we use those for convenience just because we don't want to have to remember a bunch of bits. But anything we put into the microprocessor is converted to ones and zeros. But I also said you can make up a number system. So I might ask you to do that. So look at general number systems, that PowerPoint. And if you don't know how to make up your own number system, you can ask me about that after you've reviewed that PowerPoint. Pretty simple to do. I don't think I talked about number 7 yet, a sealing circuit. So definitely before the exam, we need to get more into the logic stuff. Basically, a sealing circuit is a special circuit that you use to turn devices on and off. Imagine a button that you can flip to turn something on. I shouldn't say a button you can flip. A switch you can flip to turn something on or off. You can flip like a light switch. You can also replace that with a button, like a normally open push button that you can press like a doorbell, but you don't want to have to hold the button down to keep the machine running. So a sealing circuit, basically you can push a button and it'll latch or lock the circuit on until you interrupt the current and then it turns off. So what I'll do is I think towards the end of the week, I'm going to demonstrate the simulation software that you're going to use for lab, and I'll show you how sealing circuit works. So I'll remember how to do it, but for some reason I don't. Somebody remind me. Probably Friday, I'll probably show you the software, and I'll show you how the sealing circuit works. Or maybe I'll show you on the board. We'll see. Well, you really can't review the quizzes. This sheet, I made this when we were meeting face-to-face. But I would just say review the PowerPoints. Number 9 is pretty simple. That's the first day of class. We'll look at number 9 again today. You want to remember your basic circuit, your basic logic circuits, how you would wire those using switches and or not logic. And today we're going to look at some other derivative logic, the basic logic functions and or not. You can combine those to get other logic functions that we'll talk about today. So you want to be familiar with all the logic functions. And then remember, there was one PowerPoint where we talked about bytes and bits. We talked about kilobytes and kilobits. And we said a kilobyte, that would be a K with an uppercase B. That word kilo doesn't mean 1,000 when you refer to bytes. That word kilo means 1,024 because we're dealing with base 2. If I have a K kilo bit will be a lowercase b, then that word kilo then means 1,000 like you normally think. So I might give you some memory. I might say it's 3 kilobytes. How many individual bits is that? And you just got to know how to multiply that out and get the number of individual bits. So you just got to look at how I word the question. But there is an example of that in the PowerPoint, one of the PowerPoints we did, I believe last week or maybe the week before. So what I would say do is this, just kind of, you have these 10 points. I'm going to base the exam off these 10 points. Just kind of go through between now and, you got a couple weeks before the exam. Go through these points, and if something's not clear, let me know. If I need to go over something again, let me know. And then between now and then, I'll make sure that you guys are ready to go with the exam. So, question on the sheet. I'm sorry, I interrupted you.
Oh, sorry. When's the exam again?
I don't have it set in stone yet. I'm thinking about 2 weeks from this Friday, but I'll let you know. I'll let you know at the end of the week exactly when it is. I'll let you know by Friday exactly when it is.
I have one question about the memory section. When where was it covered? Because when I was doing the quiz, I couldn't. There's a question that says like how many sections there is in the memory. I couldn't recall it from any of the any mention of it on the PowerPoint beside when you drew the diagram of like the CPU operation.
Yeah, I tell you what, just hold on until after class. I'll have a little bit more time to think about what you're asking me.
Oh, I mean like just where would like the memory, like you said, how?
It would have been in one of the PowerPoints presentations.
Yeah.
But let me. There was, I believe, there was a diagram of the general. I want to say computer or PCU where you had the
input, CPU, memory, output, and then the logic section, I believe. Like that's the only mention of it when I look up for memory related subject.
Okay. Tell you what. Let me check. I'll check on that. Who am I talking to?
Ty. THAI.
Okay, Ty. Do me a favor. Send me a text. That way I'll remember when I get home. I'll look at that question and I'll look at the material we covered. And then if what you say, if that's the first time I mentioned it, then it wouldn't be fair to me to score that, would it? Send me a text if you think about it, and I'll check into that, and I'll get back to you in a couple days.
Okay, thank you so much.
And guys, go ahead and send your attendance text now, 494-6162 if you haven't already done it. And I want to get into the PowerPoint, and then if you have any other questions for me, just kind of hold it, and then at the end of class, I'll have about 20 minutes before my next class starts, so we can have any kind of conversation you want within that 20 minutes. Any more questions or comments on this study sheet?
No. When will the week 4 stuff be available for us?
Yeah, I tried to make it available to you last night, but somebody said it wasn't working. So when I leave, for some reason I can't log on to Canvas in this room where I am. I don't know why, but as soon as I leave here, I'll go home and I'll figure out why you can't see Canvas. I made it available last night around 10 o'clock, I think, 10 or 11, but students were telling me they can't access it. So I'm still a little rusty on Canvas, so it might be something I did. I'll check it out, and I'll make it whatever it is. I'll make sure you guys have access to it today sometime.
Okay, thank you so much.
Okay. Any more questions over the exam sheet? Okay. Guys, somebody has their mic. Make sure your mics are muted because I hear background noise. Somebody's mic is open. And I want to get into the PowerPoint. This is, oh, I got this thing blew up too far. Let me see if I can shrink it down. There we go. Okay. So this is where we kind of, I guess the rubber meets the road here. We're going to transition over from talking about this kind of just kind of academic stuff to where we actually start using some of the knowledge to program the PLC. So we're kind of moving over to that point. So this is kind of a transitional week, this fundamentals of logic. So let's get into this. And your programming, you want to make sure you get a good understanding of this week's material, especially this PowerPoint, because all your programming you do for your labs will be based on this logic stuff we've been talking about. So let's get into the PowerPoint. So what we want to do is gain an understanding of how digital logic gates work. Now, what is a logic gate? Well, you know from our discussion, there are 3 basic logic functions. We went over this the first week. There is the AND function, there is the OR function, and there is the NOT logic function. And so basically these logic functions are ways you can make electrical decisions based on how you have switches wired. For the AND, you might remember if I have switches in series, if I have 2 switches, we'll call the switches inputs, and I have some machine or some device like a light bulb, we'll call that the output. If you can visualize that in your mind, if I have 2 switches in series, the only way to get the device to turn on, in this case the light bulb, will be to close both switches. And so for AND logic, both conditions or all conditions have to be true. You looked at the truth table for that. So the truth table was a table that represents the states of the inputs and the states of the outputs for a given input. OR logic is kind of a choice. You can have either one condition true or the other condition true, or both conditions can be true. And NOT logic, well, I said that was a little stand. We kind of use a push button. We talked about that. We'll hopefully be a little bit more clear on how that function works. But the point is this: those 3 logic functions are basic functions, but we can combine those to get other logic functions that will make different types of decisions. And basically, you can see that we can make a system that can really make pretty complicated decisions if you think about it. So we'll get into this and we'll look at it. Now, does someone have a comment? I think somebody's mic switched over. Okay. So the binary concept. What is the binary concept? We know what binary is. Binary is a number system. Really what binary is machine language. It's the way machines speak to each other. But the binary concept basically means that you have one condition or another condition. But you can also think about it like this. You have certain things you want to control that can be in one state or another. For example, a light can be on or off, a switch can be open or closed, a motor can be running or not running. Anything or any system that can be in one state or another is a perfect candidate for what we call the binary concept. And these things are really, really easy to control. Now, right now, when I say control, all I mean is to turn something on or off. Well, you'll see what we mean by control. We can turn things off and on. We can turn things on and off and delay the on or the off. We can make things speed up. We can make things slow down. That word control has a lot of different meanings, as you'll discover as we go further into the course. So here's what we like to do. We know we can do logic. Well, I missed my slide. Sorry. We know we can do logic or perform logic electrically with switches. We know that. That's how it used to be done. In the very beginning, logic was done with switches, and then we moved to electromechanical relays, and now logic is done with gates. I want to talk about, well, what is a gate? Well, a gate is a solid state device, and remember the term solid state means there's no moving parts. And what the gate does is it simulates logic circuits. So if I have two switches in series and some kind of output, again like a light bulb, that represents AND logic. Well, there's a gate, a solid state circuit that performs the AND logic. And I can have a 2-input AND gate. I can have a 3-input. I can have as many inputs as I want. It's actually a circuit. You can go to, well, you can't really go anywhere nowadays, but you can actually purchase a integrated circuit, a chip, IC chip, with these AND gates on it, AND logic. So a gate is just a electrical circuit, a solid state device that mimics those physical circuits that we talked about with switches. And so for every logic function, the basic functions, the AND or not, and the other functions we're going to talk about, you have these gates. Now what this PowerPoint shows is this block representation. It's really not the way we represent these gates. Each gate has a couple things. Each gate, or I should say each logic function, which is represented by a gate, will have a symbol, a gate symbol you can use and recognize as a specific logic function. Each gate or logic function, of course, has a truth table. Each gate or logic function will have a logic circuit, which is the way you program it into the PLC. And each gate will have something called a Boolean expression. So we'll talk a little bit about that today. The Boolean expression is kind of a mathematical way. It's the algebra of logic. So it's kind of a mathematical way of representing logic circuits. And you'll see some of that today. So we already gave a definition for logic the first week. Ability to make decisions when one or more functions must be taken into account before an action is taken. So the thing to understand here is that this is the basis for the operation of the PLC. It's actually the basis for operation of any digital device. Your cell phone, a microwave, anything. But we're talking about PLCs here, so we'll be specific to PLCs. Now this next slide, I don't even know why I have this in here. I think, I don't know why I have this slide here. There's two kinds of logic. There's positive logic and there's negative logic. With positive logic, your active state, your on state, is represented by binary 1. Your inactive state or off state is represented by binary 0. And with negative logic, it's reverse. Active on will be represented by 0. Inactive off is represented by 1. Now, I first learned this in school, and just, I know I'm dating myself, but I graduated from college in 1996. Of course, I have several degrees, but back in 96, I finished up school, and I was in school all through the 90s and even the late 80s. I was in school, and I learned about negative logic, and since then, since let's say the beginning of the 90s until now, I've never seen negative logic used anywhere. So I remember reading about it in my textbook, but it's always positive logic. So I probably need to omit this slide. We'll only use positive logic, and honestly, that's all I've ever seen. So here you go, and or not. We talked about this in detail. I represented these logic functions with switches and buttons hooked up in series or parallel, and you'll see that we can combine a series and parallel circuits to get more complicated logic functions. Of course, you won't do that with switches, but you can do it with the gates. So you've seen these, but here's the thing. Each one of these, as I said before, you want to know each one of these has a gate symbol that represents the logic. So there'll be a logic symbol for and, a logic symbol for or, and there'll be one for not. Each gate also or function has a truth table, which we've already went over a little bit, but you want to be familiar with the symbol. You want to be familiar with the truth table. You want to be familiar with the logic circuit that you'll program into the actual PLC, and you want to be familiar with the Boolean expression. So it's nothing you really have to memorize. I think as we go through and you guys start working with this stuff, you'll see. And the good thing about logic is it's logical, no pun intended, but it is. Once you see what's going on, this stuff is actually pretty easy. It's pretty simple and actually kind of enjoyable, to be honest with you, when you start messing around with this stuff. Let's get into some of the actual symbols for the gates. So instead of having switches that I draw in series, when I want to represent AND logic, I'm going to use this symbol right here. Now, typically in electrical engineering, when we draw devices, we draw these representations of certain devices, and we put them together on paper to make a circuit. That picture is called a schematic, electrical schematic. Well, typically on schematics, any kind of device, like here a gate or maybe an amplifier, any kind of device, we typically draw the inputs on the left and the outputs on the right. So you'll see here, I kind of followed that. Now, for some reason, I didn't follow it in the other slides. I think I mentioned to you guys back in 2004, I got pissed off at the bookstore because they kept raising the price of my book, the book that you guys buy. I mean, it was ridiculous. It kept going up in price. So I said, you know what? I'm going to throw the book out. I'll just put everything on PowerPoint. So these PowerPoints are actually quite old. I wrote these back in 2004. And I think I couldn't get when I tried to make the other gates, I couldn't get the inputs on the right side. I don't know. You'll see what I'm talking about in a second. But what I'm referring to here is that you'll see that I have the inputs on the left and the outputs on the right. And typically, we represent inputs with letters of the alphabet from the beginning of the alphabet. We represent outputs with letters from the end of the alphabet. So you might have A, B, C, D, E, F for inputs and X, Y, Z for outputs. Just kind of like you do in math. So here's the symbol for the gate. Now, the actual AND circuit is a solid state device that you can't see what's inside of it. The circuitry is actually microscopic. If you can actually open up a gate and look under a microscope, they use these solid state switches, these special switches called transistors, to build these logic gates, these circuits. But we don't really have to concern ourselves with that. We just have to kind of abstract from that and just be familiar with this gate symbol. So there's the gate symbol, and then here's what I meant by the truth table. You want to know this like you know your address. And it actually makes sense that if you think about switches in series, the only way to get an output, actually I think I show it on the next slide. So here's a good way to understand the AND gate. Understand it like this, using the circuit diagram. So you want to understand the circuit diagram, but remember this when we talk about the AND function. So here's kind of what's going on inside that chip. You have these inputs, and this is a 2-input AND gate. You can have AND gates with as many inputs as you need. An AND gate has to have at least 2, but there's no limit to how many it can have in theory. So we've already went over this, though. We see that our inputs here, I'm showing on the gate, we got switch A and switch B. So they represent these switches here, switch A and switch B. So the actual circuit is the actual one with the switches. If I close switch A, close switch B, the light bulb lights up. And so the truth table says that when A is closed and B is closed, there's a 1 over here on the output, which means that's when the condition is true. Well, as we said many times, the AND condition is true when both inputs are true. So instead of drawing this circuit, we would just show the logic gates, and I can start putting bits right here. If I put a 0 on any input, then my output is 0. The only time I'm gonna, on this gate, the only time I'm gonna get an output of 1 is when I have what you see now on the screen, a 1 on each input. So again, remember how the switches work, but we'll only look at these gates, and then we'll take those gates and transfer those gates over to the PLCs using a special language called relay logic. Now, here's what when I was talking about, I had the inputs drawn the wrong way. You see, really, I should have this flipped over. The inputs A and B should be on the left, and the output should be on the right. I think when I was doing this in PowerPoint back in 2004, my PowerPoint wasn't behaving correctly, and I couldn't get this thing oriented the right way. So just imagine it was flipped the other way. And this is the OR gate. Now, in the PowerPoint, when I drew this OR gate, the actual where the Y is, the output, there's usually more of a point right there. It looks like a Star Trek sign, if you know what that looks like. But this is the closest I can get to it. So if you draw it like this, I'll know what you mean. So again, you have the symbol, the gate symbol for the OR, and then you have the truth table, which we've already talked about. For OR, you only need one true condition or one closed switch to get an output. So we can represent that with a circuit like this. Switch is in parallel. If switch A is closed, then you have a path for current to flow to light the light bulb. If A is open and B is closed, you have a path through B to light the light bulb. Or if both switches are closed, you have a path to two paths to light the light bulb. So we looked at the truth table for the OR, but again, you want to think about it like this with the switches, but you want to remember this symbol right here, because this is the way we'll refer to it for the next couple of weeks in class. So we looked at the AND gate and the truth table. We looked at the OR gate and the truth table. There's one more of the basic functions, and this is the NOT gate. So we represented that with a normally closed push button, but here's the actual logical symbol we use to represent the NOT function. It's also called an inverter. It's called an inverter because what this chip does, what this gate does, is it flips the bit. So this is the only gate that has a single input. All the other gates have to have at least two inputs. They can have as many as you want, but they have to have at least two. Well, the NOT function only has one input. And so let's kind of dissect this a little bit. Notice over here on the left, I have input A, but over here on the right, I got that A, and it has a bar over it. Well, that's called A NOT or NOT A. You can say it either way, A NOT or NOT A. And what that represents is the variable A can take on any value on the left. Well, remember, we're dealing with binaries. When I say any value, that means that A can either be equal to a 0 or A can be equal to a 1. If A is equal to a 0, then any variable with a NOT over it will take the bit and flip it. It'll change it to the opposite bit. So if on the left, if A equals 0, then when it goes through the inverter, NOT A is a 1. If A equals a 1, then NOT A would be a 0. So this is just kind of a mathematical way of showing that. You see a variable with a bar on it, it takes the original variable and then changes the state of it. And you see that in the truth table over here, right? So if A is a 0, then NOT A is 1. And if A is a 1, then NOT A is a 0. Now, let me tell you the way I think about this. It's very helpful to think about this. Let me actually go to here. So if you look at this gate closely, you'll see there's a bubble right here. This little bubble. It's called a state indicator. A state indicator. And here's what I do. When I actually think about zeros and ones moving through from left to right through these gates and chips. And what you want to think about is when that 0 or 1 hits this bubble right here, that's when the inversion takes place. So think about like I got a 1 right here on the inputs. Here's a 1. Well, that 1 is going to be fed into this circuit, this gate, So the one's here, and it's going to move in. When that one hits this, then that one flips over to a 0. Or if I start with a 0 over here, when it hits that state indicator, that's when the inversion takes place. It flips that to a 1. Now, why am I thinking about it that way? Well, see, what we're going to end up doing is we're going to combine these basic functions to get what we call derived logic functions. So kind of like chemistry, you can take the basic elements and put them together, mix them together and get compounds. We do the same thing with logic gates. We can take the basic gates and put them together to get other logic functions. And if I want to use a NOT function, instead of writing the whole gate out like this, instead of writing the triangle and the little state indicator, what they'll do is they'll just use the gate and then they'll just use the state indicator. And you'll see an example of that in just a second, and I'll make sure I'm clear on what I'm talking about. Okay, so we looked at the basic gates, and or not. We looked at the symbol for each of those. We looked at the truth table for each of those. And so let's look at the circuit. And I showed you this circuit before in the first week of class. When you think about the NOT function, you use this normally closed push button. And hopefully looking at the truth table, it makes sense. This not pressed and pressed. Not pressed is a 0. Pressed is a 1 is the way to think about it. And so if this is a normally closed push button, if the button is not pressed, it's a 0, and the light's on, that's a 1. If the button is pressed, then the contact will open up, and then pressing the button is equal to a 1. So of course the light will be off, which then is represented by 0. So it's kind of hard to explain NOT, but I think this circuit and the truth table, if you look at these, really is kind of self-explanatory. You kind of get it. All you really need to know about NOT is this. Whatever bit flows through that NOT circuit, when it hits that state indicator, it's going to flip to the opposite bit. And then you'll be good to go.
Kind of just to make sure I understand NOT correctly, like a good example, would that be like an emergency stop button, basically, where when it's not pressed, everything runs smoothly, but as soon as you press that button, everything kind of shuts off?
Yep.
Okay.
That's a perfect example. Who is that?
It's Evan.
Evan, I'm going to steal your example and use it.
Okay.
Okay, let's see. Okay, now, remember I said we can combine gates? Well, here's an example. I can take an AND gate. I'm going to try to draw an AND gate with my mouse. So here's my AND gate. And I can run that AND gate to an inverter. So what I have, I have the AND part right here, and then the NOT part right here. So what they do is they combine these two gates. They combine a NOT and an and they call it a NAND gate. A NAND gate is a NOT AND gate. A NAND gate is a NOT AND gate. Now remember, look at this truth table right here. Look at the output right here. Look at the output, and then go back to the. Let me go back to the output for the AND gate. Where's my AND gate? Look at this table. Look at this. Look at this output. So the AND gate, the only time I have a true condition is when both switches are closed. Well, if I take this right here, this column, let me erase this. How do I erase? Okay. If I take this column and if I knot that, let me see if I can draw. Oops. I'm trying to draw with my mouse, and this is hard for me to do. So if I take that Y and I knot that, that means I would invert these bits. Because remember what we did with that NAND, we just put an inverter right here. We put that inverter right there. And so what's going to happen is these bits, this column right here, these bits, that's right here. That's right there. And when those bits go through that inverter, each one's going to be flipped. That'll be changed to a 1. This will be changed to a 1. Let's change to a 1. Just change to a 0. Well, that's exactly what you see if you look at the truth table for the NAND. So basically, it's the opposite of the and. So you can have logic or you can have the opposite logic. You'll find out that this NAND and this one more gate that kind of related to the OR, the AND with the NAND and the one related to the OR, you can do almost anything with just those two gates. We'll talk about that. They're what we call universal properties. But just remember I mentioned that instead of actually drawing, I can take the AND gate. I can take the AND gate. It's a terrible looking AND gate. And then the OR gate. I mean the NOT gate is what I'm trying to say. There's the NOT gate. Well, instead of drawing this gate right there, let me just draw the state indicator right here. So this is a combination of the and then the state indicator from the inverter for the NOT. And instead of drawing that whole triangle, we just draw a little bubble. That's why earlier I said I just think about when those zeros and ones are flowing from left to right through a chip. Anytime they hit a bubble, they're gonna flip state. They're gonna change states. Okay, so well, if there's a NOT and, I can also take that NOT. I don't know why all my OR gates are pointing the wrong direction. I really must have that screwed up. Anyway, I can take an inverter and a OR gate. And I have a NOT OR gate or a NOR gate. So if you remember for the OR gate, the output was, I had a 0 and every other one was a 1. Well, here if I invert that, I get a 1 and every other one was a 0. So why do we have these opposite gates? Well, you'll see they actually make life a lot easier by having AND logic and then the opposite logic. So we have, these are derived gates. The NAND and the NOR are derived gates. So you take the basic logic gates, the basic OR and NOT, put them together, you get a derived gate. Now, OR is kind of interesting. Look at this one. Look at the next one. Look at that one. Compare this. That's an OR gate, but it has this little line on it right here. See that? It has that on it. It's the same as the one before that I just showed you. There's a NOR gate, but I was looking for the OR gate. Where's my OR gate? So look at this OR gate. So that there's a, called the XOR, they put this little bar right here. And look at the truth table for this. So for my OR gate, of course, my output column, these are all ones. They're all ones. When I go back to my NOR, look at the output for the NOR gate. I mean the exclusive OR gate. Look at this. So it looks exactly like the OR. I have a 0, I have a 1, I have a 1. The only row that's different is this one right here. So that's why they call that the exclusive OR, because it excludes the condition where both inputs are true. So there's two kind of ORs. There's just a regular OR, I'm doing air quotes, a regular OR, and then there's the exclusive OR. The exclusive OR excludes the condition where both inputs are true. And you might think to yourself, well, why would you want to do that? Well, here's why. In the English language, what we're going to end up doing in this class, in theory, what I should be able to do, if I don't know anything about PLCs or logic or programming, if I know absolutely nothing about any of that stuff, in theory, I should be able to, I know how my factory should work. My assembly line, my industrial process, I know how it should work. In theory, I should be able to write a description of how things should work, i.e. the logic, hand you that description in words, in English, and you should be able to take those paragraphs and convert it over to basically a working logical program, which you can put in the PLC. And the problem is that in English, and means, at least in logic, and means a specific thing. And means both conditions have to be true. But the English word or, when you say or, sometimes you mean one or the other, and sometimes you mean one or the other or both. So if I say something like, this is probably going to be a bad example. Do you want, I don't know. I can't think of an example. Oh, let me give you an example. I'll do the opposite example. So here's an example of the exclusive OR. You know, when you go eat, you go out to the restaurant and you eat, and you look at the menu, and it says you can have an entree or you can have a super salad. Well, what they mean when they say super salad, they mean this kind of order. You can't have them both. If you want both of them, you got to pay for something. But you can have one or the other, but not both. There's an example of the exclusive order.
Could you say, like, if you want water or coffee, I guess, for both?
Yeah, you can something like that. If you want water or coffee or both, and I actually did that this morning. I wanted orange juice or water, but I actually got both of those. I wanted both because I eat orange juice with my breakfast after this class. When you guys are done answering questions, I have about 15 minutes to eat breakfast, and then I consume orange juice and water to take my vitamins. So yeah, that's a good example. So let me say something, guys. I'm not going to tell you what it is, but on one of your programs, you want to remember this OR gate. This XOR is very special. It's going to come back at you on a program on one of your labs, and it's going to rear its head a couple times. This one's pretty powerful, simple but powerful. So we'll come back to that. Okay, let me pause. I'm going to run out of time because there are some exercises we're supposed to do. Not a big deal. We'll just do them on Wednesday because this week's kind of light with material anyway. But I want to go. Does anybody have any questions so far on any of these gates? Because I want to get into the Boolean algebra and the rules and all of that. Anybody have any questions on any of the gate stuff? Anything I talked about so far? Okay. Well, so here's what's going on now. What we're doing is we started out on week 1 when we first talked about logic, showing you switches in series to represent and, switches in parallel to represent or, normally closed push buttons to represent not. And you can imagine that I can take switches in series and switches in parallel and combine those into more complicated circuits to represent more complicated logic. But what we really want to do is abstract from all the hardware. We want to abstract from all of that and just think about these circuits kind of mathematically. That way I don't have to build anything. I don't have to deal with anything I have to touch. We can just think about it kind of mathematically. And so there's something called Boolean algebra, which is the algebra of logic, or the algebra of base 2 systems. So this is kind of cool because once we represent a logic circuit mathematically, then I don't really have to worry about the circuit anymore, the actual physical circuit. And I can do things with the equation that I get. I can reduce the equation, which would result in a reduced logic circuit. I can do a lot of stuff once I represent it mathematically, I can do a lot of stuff with the logic that it would be difficult to do if I only had the physical circuit. I shouldn't say difficult to do, difficult to see is a better way to say that. So this slide, I would mark it, this one right here. Now there's more to this slide, but this is an example. Remember I said earlier that for each logic function, there's a logic symbol. So here is the symbol for the and, here's a symbol for the or, but it's drawn the wrong way, and here's a symbol for the not. So I think these are easy, we got that. But over in the next column, the Boolean equation. This is the way you write these logic functions mathematically. So for this AND gate, I can draw the gate or I can write this. Now let me say something about the AND, Boolean expression for AND. Think of that like the multiplication operator, the little dot operator. I didn't show that on this PowerPoint because I probably didn't know how to make a dot at the time. But there's really a multiplication sign between the A and the B. So this should really say A dot B, and the dot is the operator for AND logic. Just like right here on the next one, this little cross is not a plus sign. That's not A plus B. You read that A or B. The plus sign, what you think of as an addition sign, is the operator for OR logic. So just like I have a plus sign there, there's a little dot in between the A and the B for the and. Now, having said that, any way you can represent multiplication in regular algebra, you can represent and in Boolean algebra. So what I mean by that is this. It's proper to write A dot B when you want to multiply, like 2 dot 3 is 6. I can put the little dot there. So I can write A dot B, and that dot represents and logic. But any way you can any way you can show multiplication, you can also show and logic. So you know how you can take the 2 and the 3, and instead of putting the dot between them, 2 dot 3 to get 6, 2 times 3 is 6, you can put the 2 and the 3 in parentheses. That means multiplication. Well, that also means anding. Or you can take the 2 and put that in parentheses, but not the 3. That's still anding. So any way you can represent multiplication in regular algebra, you can represent and logic in Boolean algebra. And again, I'll show you, probably won't have time to do it today, but when we work the example problems, I'll show you that. I'll show you what I'm talking about. And then, of course, we already talked about that bar. That represents the inversion or inverter. And so that's read A naught or not A, or A bar, however you want to say it. Just know it's flipping the bit. Okay, so this is an important slide. Mark that slide and then this one. So here are derived gates. Here are the Boolean expressions for derived gates. So if you remember, this NAND gate is an AND gate and a NOT gate, right? So what I do, this right here is, there's my and then I got to NOT that. So I NOT that, and that bar represents a NOT AND gate. So I write that A equals right here, Y equals a bar AB, or I would say not AB. So I got the NAND, I got the NOR. The NOR is just the OR. There's the OR function. And I got to NOT that whole expression. And then the XOR. Remember the exclusive OR? The one that excludes both, where both conditions in OR are true? The way you show an XOR is it's the plus sign, but then you put a circle around it. And I couldn't get that circle centered, but imagine that plus sign is centered in that circle. So this slide, you want to mark that, make sure you understand, and I mean, we're going to use the hell out of this stuff, so you'll know it. I'm not even worried about you guys knowing it. You're going to write this stuff down, but just put a mark by it so you know to study it. Go back and look at it, and you make yourself familiar with it. Now, there's these laws. Well, there's laws and there's rules. So these are the three basic Boolean laws. So just like in regular arithmetic, you have commutative property. So multiplication and addition are commutative, which means you can move the numbers around when you multiply, or add, and it doesn't change the outcome, the answer. Well, in Boolean algebra, we have the same thing. In associative laws, basically, associative law for addition and multiplication. Doesn't matter right here if I add the A and the B first and then add C, or do it the other way. And the same with multiplying. So these first two, the commutative law and associative law, are exactly like regular algebra and arithmetic, exactly the same. And this distributive law right here, that probably makes sense to you. That makes sense. So all of these, I can look at all that, I get that. Now this was a little weirder. This one right here. This one, you guys are probably a lot smarter than me. So when I look at that, I cannot see that. I can't see it. What I can do is put both the left and right side of this expression in the truth table, and I can prove that they're logically equivalent. So I know this is right. I just, in my mind, I just can't see it by looking at it. I'm not that swift. But that one says this law only holds in Boolean algebra. So there's actually these laws, and then let me get out of this for a second. I want to show you the rules. I got some rules. Where are my rules? My rules are right here. Look at these rules. So it's actually, now you might have to expand that to look at these rules. So you got the laws, the 3 laws we just went over, but then you got those 10 rules. Now, if you guys were electrical engineering students or EET students, you'd have to memorize all of this stuff. You'd have to know this like you know your address. You don't have to for me. I mean, I'm going to give you one homework problem where you'll use this sheet just so you know that these rules work. But after that, what you use these rules for is when you have a complicated logic expression. Now remember, any logic expression is derived from a circuit. So a complicated logic expression came from a complicated circuit. Maybe you got a lot of gates and or not gates. What you can do is use these rules and laws to reduce the mathematical equations down to basically fewer terms. Fewer terms mean fewer chips or gates in your logic circuit. So you can actually use this for simplification. So my point is this. We're going to do like one homework problem where you have to solve one of these equations using these rules and laws to simplify a logic expression. But then I'm going to show you another way based on grade code. Remember I told you when we looked at grade code, we'll use that later in the semester. I'm going to show you a really slick way where you don't have to know any of these rules, and you can take a complicated Boolean expression and you can reduce it down to simplest form. As long as you follow the steps correctly, you're guaranteed to come out with a minimized circuit. So that'll be coming. But for now, just realize that these rules exist, and you'll do some homework. One of the homeworks you'll do, you'll use that. I'm running out of time, so I want to get through this PowerPoint. Why is this not switching over to my, wait a minute, hold on a second, guys. Oh, here we go. We're stuck on the, let me finish this up and then I'll stick around in case you have questions, and let me see where we left off. All right, so we were right here, and then I showed you the equations there. Now, if we have more time today, what we will do is some practice problems, and when I'll figure out why you guys can't get into the module, but this is important right here. This is really, that's three reallys, really important. It's called the Morgan's law, because you're going to use this to basically change one set of gates to another. And this is actually used a whole lot. So let me just show you what it is here. So given this expression right here, you might recognize this now. This right here is a NAND gate, and this right here is, this is not a NOR gate. The NOR gate would have a bar all the way across both of these. This is actually a negative OR gate. When the bubbles are on the inputs, like right here, look at this. This term right here represents this gate. This side right here, I have a OR gate, but since each individual letter is knotted, then that means the bubbles are on the inputs. You know, the NOR gate has a bar all the way across here. The bubble was on the output. But on this one, the A is knotted. This is how you knot the A, which gives us this. And the B is knotted. This is how you knot the B. You end up with this. So this right here is not a NOR gate. This is actually called a negative OR gate. But what De Morgan says is that this side of the logic equation and this side are logically equivalent. So that means that this gate can be replaced by this gate or vice versa. And that turns out to be really important. Guys, it's 10 o'clock. I only got like about 3 more minutes of talking to do. So if you have another class and you got to go ahead and sign off. Just don't forget to send me your attendance. Text 494-6162 with your attendance. I'm going to continue talking, and if you missed the tail end of this, you can go to the videos and watch the video on what I'm going to say here for the next few minutes. So if you got to take off, go ahead and take off. Now, the Morganizing, there's a really easy way to remember De Morgan. De Morgan, this is De Morgan's theorem. You can De Morganize using De Morgan's theorem. I can state the theorem, but there's a really easy way to remember it. All you gotta do is remember, break the line, change the sign. Write this down somewhere. break the line, change the sign. If I say, all right, student, I want you to demorganize this expression. What I mean is break the line, change the sign. And what does that mean? Well, look, I have one solid bar right here. So I'm going to break the line, so that line is broken now. And remember, there's a dot right here in the middle. There's a dot. And I'm going to change the dot to a plus. So if you break the line, change the sign, you get an equivalency that's basically a statement of De Morgan's theorem. So I can do this with the NAND gate, or I can do this with the NOR gate, right? So again, you can follow this if you want to. You can go through the logic. You can follow this diagram here. It all makes sense. But if you break the line, change the sign, here I have the OR and the bar. I break the line, and I change from a OR change the sign, then you're demorganizing. Just remember, break the line, change the sign. And then finally, I want to say, if we have more time, we do this kind of thing, where you come in, I'll give you these gates, and you want to kind of look at the gate circuit, and from the circuit, develop a Boolean expression from the circuit. So we'll do some of this on next class on Wednesday, but basically it's this. So I'll start with this circuit, and then I'll go to this, the A and the B. They gave me A dot B, and then I go to this, the A and the B. I'm ORing that with C, so I get the this term right here, the A, B flowing into this, which gives me this term, and I get C flowing into this. And what this gate is going to do is take this and the C, and it's going to OR them. It's going to OR them together. So you'll do something like that for me. Next time we'll practice doing that. And that's one of the handouts I have on Canvas, but I realize you guys can't get to it right now, but I'll take care of that. So really, guys, that's all I have for you. That's it. I'm going to stick around in case anybody has any questions. Let me get out of this thing. Okay. So if anybody has any questions, I'm going to stick around. Other than that, guys, have a great rest of the day. Stay safe, and I'll see you on Wednesday. Anybody have any questions for me? I'll stick around for a few minutes, and I'll take your questions.
Yeah, Professor, I had a question about the quiz.
Okay.
For question 1, it was like the input and output modules provide equivalent of eyes, ears, and tongue to the blank. On the slide, it said the brain of the PLC. Would you accept that? I know it was wrong, but I wasn't sure if I would put that or the CPU.
It was a CPU. Did you put brain?
Yeah.
Yeah, I'll take that. Can you do me a favor and send me a text so when I'll know what's your name?
Jack.
I can't hear. Spell it for me.
Jack.
Oh, Jay. You said Jack?
Jack, yes.
Okay, and that was number 1?
Correct.
Okay, yeah, I'm supposed to be looking at the quiz for another student. That was the other quiz, though. Yeah, I'll take a look at that. And you said brain, because I had that on the slide. It should have been CPU. But yeah, I'll fix that for you.
All right, thank you.
No problem. Anybody else?
Yes, I had the same answer for number 1.
You said brain?
Yeah, brain.
Okay. I got it. What's your name?
Christian Steffet.
Christian. Okay, Christian, I'll take care. I'll fix it.
Thank you.
Okay, buddy, no problem. And who else is out there? Tucker, Jacob, any questions?
We just send the text to the same one we've been sending for attendance, correct?
Yeah.
Okay.
Yeah, just send it to that one. Send it twice though. Send the attendance, and then send me a second text because Everybody sends the attendance at once, and they're all scrunched together. But if you send it again, it just works out better. And if it's not changed in like a day or two, then just send me another text. Okay, all right, guys. Well, then I'm signing off. You guys stay safe. I'll see you Wednesday.